Okay, so for record, all students are in the class. Okay, just a refresher for this chapter. The only formula that you should remember is F equal to KD, right? We repeat so many times, and then be careful on the capital F and small f. Okay, capital F stand for global coordinate or global system. It means it's an assembly system. Then we use capital F, capital K. If you're looking at very, very small or single element, then we use a small f and small k. D still remain the same. D is a displacement. K is a stiffness. F is the force acting on the spring. And again, this spring is just is a free body diagram that we extract from maybe an aluminum bar or a medium or a structure that able to stretch, right, and act as a spring. And this is an example that we have been going through. So if you're looking at individual spring with 2 nodes and 3 to move around in the x direction only, then the matrix we will have in this form. Means you'll get 2 times 2 K matrix, 2 forces, 2 displacement in x direction only. Okay. And then we also know in later chapter, we expand this one to 3 forces. 3 forces, then you have 3 times 3 K matrix and then 3 displacement. Okay. We have been through on the derivation on the matrix here. So we have changed a general matrix into K form, okay, into a stiffness matrix K form that apply to the example. So on the left is force, in the middle is stiffness coefficient. So here we can see that we have a symmetry matrix here. We have positive K, and positive K, and the displacement on the right. So this is the matrix for a spring structure element. Again, you'll see a small f on here. Okay. And then we look at a higher level where we are looking at 3-dimensional or 3 degree of freedom cases. This one, you can look back. This one is in your tutorial, question number 8. We have gone through. So before this, we have been through a 2 times 2 matrix. And now, because we have 3 forces or 3 unknown for your displacement, our stiffness matrix, we have modified a little bit from 2 times 2 become 3 times 3. The process is called superimpose. Okay, superimpose. The procedure already in the slides. So I already explained using this example how we convert from 2-dimensional, from these 3 equation, we convert into a 3 times 3 K matrix. Okay, so if you're still not sure, go back and view the video already posted on YouTube and also on the Moodle platform. Go and view it again if you're not sure. Okay, so this is a reading material for you. We already explained how you convert 2 times 2 matrix into 3 times 3 matrix. I already explained. So again, if you're not sure, go back to the video in our last lecture. Okay, this is the slides that go into very deep detail on the step-by-step guidelines. So I already explained in a more simpler way. Then we also talk about what is homogeneous, what is non-homogeneous. Homogeneous means the structure do not move, or that particular point do not move. Your U, one of your U is 0. If it's non-homogeneous, then all the points are moving. Okay, or you have displacement for all the points. So we have gone through example on homogeneous. And also we have gone through example for non-homogeneous. So make sure you understand all the mathematical symbol. And then I'll give you one homework to go and look at is the inverse matrix. How do you do inverse matrix? The negative one, how when you move your K matrix from the left to right, you need to inverted the matrix. So there's a processing the matrix. So if you're not sure, go to Appendix A and look at the procedure. And also this is 2 times 2. So when it comes to your test or exam, it will be 3 times 3 matrix. So 3 times 3 matrix the procedure a bit different from the 2 times 2 matrix. So don't mix up with the 2 times 2 inverse matrix and 3 times 3 inverse matrix. The procedure a bit different. Okay, it's just a reminder. Yeah, this one is just a note there. There's Appendix B in the Moodle, so you can go and download and read through how do we solve a simultaneous equation. Okay. Right, today our objective today is to solve 3 tutorial questions, which is in your handout. It's question 10, 11, and 12. Okay, if you can solve it a bit early, then we can end a bit early. All right, but however, important is that you understand what we are discussing. Okay, we look at question number 10, or on your screen, you will see that we're having a set of spring which align linearly or in a series. Okay, so we have 3 spring here, and then the stiffness was given, each of the spring was given. So if you see a symbol 1 and circle means element 1, spring number 1, spring number 2, and spring number 3. We have your stiffness matrix. K1 means stiffness for spring number 1, and so on. And you will see a small circle in the diagram where it represents an individual node, NOD node. So we have 1, 2, 3, 4. 4 nodes with this label accordingly. 1 is on the wall, 2 is on the wall, 3 is between spring 1 and 2, node 4 is between spring 2 and 3, and also there's a hidden forces that you can see in the middle where it's hidden at point number 4 or node number 4 with a value of 5,000 newtons. So this kind of tricks will happen in test or exam. So be careful to read carefully when you come to a question. Normally there's a hidden force inside the structure, so be careful. So the question go like this. So you have a assembly of spring, and the question asks you to obtain a few things. So you have A, B, C, D, and you read through. So the force 5,000 Newton is applied at location number 4 in X direction. Spring constant is given. Not 1, not 2 is fixed, means it's joined to the wall. All right. Now we need to find 4 things. 1 is global matrix. Okay. Number 2, displacement. Number 3, reaction on force on node number 1 and 2. Number 4 is the force in each spring. So we need to solve all these things. Okay, before we start, I need to ask you a few questions. Okay, let me ask you one question. Okay, Lai, this question is for you. So for A, the global stiffness matrix. So global stiffness matrix, what symbol that you use? You use capital K or small k? Lai, are you there?
Yes.
Yeah. So if you look at the screen, so the question asks for section A, asks you to find the global stiffness matrix. So you have big K and small k. Lloyd, can you recall
K.
the
Capital K.
capital K? Correct. Okay, then number 2. I ask Singi, B, the displacement, the word displacement here, what is the alphabet that you use? And this one is in X direction.
But it's like S X direction is U.
U, correct. Okay, excellent. So number 3, C. I'm going to ask Katana. So Katana, if you look at instruction on section C, he requests for the reaction force. So reaction force, what symbol will we use? He asks you reaction force at node 1, 2. So we are using capital F or small f?
1 and 2.
Yeah.
This is a capital F.
Is a capital F. Why capital F?
Wait.
Yeah, it's a capital F. Correct. correct. Yeah. Okay. So, and then the number D, forces in each spring. Each spring means we look at a small element, then we have a small f. Okay. So at least before you start solving question, at least in your mind, you know what equation that you need to find. That is important one. So before you start anything, make sure you know what the question trying to ask you. All right. Now, the procedure is quite simple. So before you start anything, you express Stiffener matrix for each element. Okay, you recall the general equation for element. You recall that what we learned. So you draw out a spring structure, and then and this spring is free to move around, where point 1 is free to move, point 2 is free to move in x direction. It gives you this general Stiffener matrix. So you have small f on the left, small k, and the displacement u because it's in the x direction. And yeah, so this basically come by pair. So in exam, if you draw this one, if you draw the single element plus this general equation, these two, maybe I will give you 2 marks. Minimum, you'll get 1 mark for this general equation before you solve anything. Okay, so this is how you score marks in this module. So just give you some general idea. This module, what I'm going to test you is your understanding rather than the value that you're supposed to solve. I'm testing your understanding. Okay. So the first step is to call the standard element formula. So you pull out a spring, and then you pull out the matrix equation for individual spring. So now the first one, you look at this component. I'll draw on the screen here. So what you have is you draw a spring, and then you input the node. So this is spring number 1, node 1, node 2. You're given k here. Value is given. So you just convert what you see from the general equation, you convert into the application of the problem here. So how you write the notation, mathematic notation, you know that because before we learn, we know that F equal to KD, and I always remind you guys.
Excuse something. On this matrix, 1 to 3,
Yeah.
and here on the spring that
sorry,
you just
I'm writing the wrong one. It's not 2, it's 3. 1, 3, correct. Yeah. Go ahead. Your question, go ahead.
No, that was what was confusing me.
Oh, so I already explained, right?
Yeah.
Yeah, okay. So yeah, actually it's I write the wrong number here. I'm referring to 1 and 3, the first one, 1 and 3, yeah. So it's not 2. I write the wrong one. Okay. So we're looking at first element. So you have a node 1 and node 3. So just back to fundamental, you know that your F is curly, K is a bracket, square bracket, and displacement is curly. So now we are looking at the K component. So how you write the notation for element 1? You write K with a small bracket of 1 to represent element 1. And then how you write the matrix. Okay, this one is in the exam, you don't need to write the 1, 3 beside the matrix. You don't need to write. So what I'm looking for in exam is that you write like this: K equal to 1000, negative 1000, negative 1000, and 1000. The labeling here is just to let you know that because before this, I did show you guys that we actually can break the matrix into location. So first row, first column here is referring to node 1 or displacement number 1, and node 3, and node 1 and 3. Before this, I write 1, 3, 1, 2 here or 1, 3 here. Okay, so it's the same. So it represents the row here. Okay. On the slide here, I just give you some guidelines of how you refer to the number. Okay, in exam, you don't need to write 1 and 3. Just a reminder. This is just a signboard for you so that you are clear the location of the matrix. Because later on, we're going to convert 2 times 2 matrix into 3 times 3 matrix, the superimposed procedure. Okay, that's why we are labeling all these things. All right. Any questions so far for the first element on the K matrix? Ask me now if you're clear or you're not clear on the screen. Something on the screen that you're not sure, ask me now.
So, sir, on the, is it the previous lesson?
Mm-hmm.
When we were, I think we were solving an example, or the steps actually.
Okay.
The first step was to separate nodes and spring elements, but here we have the nodes and spring elements all in one.
Yeah, we haven't gone to that step yet. Now we look at now we look at the Stiffner matrix only. Yeah, because why? Because section 1A, it asks you about global Stiffner matrix. So we straight away jump to the Stiffner matrix component. We don't need to like derive from the beginning. Yeah, the previous example I give you in the last lecture, I give you the whole set of the solution. So this one is individual component where we focus on on the Stiffner matrix. So that's why we jump into that particular section. Yeah. Okay. All right. So we move to the next steps. So after we find the first element, Stiffner matrix of first element, we continue with the second element. So repeat the same procedure, where now you look at the second element, node 3 and 4, and K is given, K number 2. So you're still looking back at the general diagram on the left-hand side here on the screen, and then you apply to what you see on the individual element that you draw on your paper. You just transport or import all the known value inside the matrix there. Again, in exam, you don't need to write the 3 and 4 beside the matrix, right? You can use pencil to write, but when it comes to answer, don't write it with a pen or your real answer. This is just a signboard or just a guideline for you to identify the numbers. Okay. Yeah. Okay. Any question on element number 2? Anyone you not sure how to get 2000, negative 2000? here. It's the same principle that what we learned for element 1. Now we import what we learned so far, apply to element number 2. Lai, you okay, Lai?
Okay.
Okay, all right. So if you're not sure, ask, yeah, because I want all of you score very high for this module. Yeah. Okay, same, you apply for element number 3, same. So you pull out element number 3, and you look at element number 3, you have 0.4 and 0.2. And stiffness matrix number 3 is given. So you just apply what you see in the diagram, and then you apply for the stiffness matrix here. You just import all the value inside there. So that's why you get 3000, negative 3000, negative 3000, and 3000. Again, in exam, you don't need to write the 4 and 2 beside the matrix. This is just a guidelines for you to know that the location represent that particular value. Okay. Of course, you still want to write, it's all right. You use pencil or other colors of pen to make it as a guidelines also, right? Yeah. Because matrix, you don't have the number beside the bracket. Right? Just let you know. Okay. Now we have so far we have the 3 matrices for individual element. The first, again, section A, it asks you about global stiffness matrix, meaning you are finding the capital K in the global scale, and you need to sum all the small k. Okay, this formula you see in the previous slides. Okay, now is a time for application of this equation. So how you combine k 1, 2, 3? This procedure is called superimpose that we discussed in the previous class. So what you do is you are using all the numbering that you do beside the matrix here, and you combine them. You combine them in one matrix. So you want to combine everything. What you do is that you put a very big matrix, and then you build a invisible line in a matrix like this. Okay, so you know that you have 1, 2, you know that your numbering is you have 1, 3, 3, 4, 4, 2. So actually this is the wrong one, because you have four number here. Okay, so you need to expand your matrix into 4. Okay. Okay, of course, in exam you don't use your pen to draw this line. You can use pencil to draw, but don't use pen to draw. When you use pen to draw, it means that is your final answer. Okay, so you label the location. Oh, I cannot use the circle. You just label 1, 2, 3, 4. 1, 2, 3, 4. So you can put number either on the right hand side or left hand side, doesn't matter. Okay, 1 on the top here means this column, 2 means this column, 3 this column, 4 this column, and 1 means first row, 2 and so on. 2 is the second row, 3, 4, so on. Okay, so again, 3 times 3 is a wrong approach. You need to look at the unknown or the stiffness matrix that you have. Here we have four location coordinate in the matrix. So we just apply. So how do we fill in the space here? So the first one, you look at number 1. 1, okay, I make a bracket here. 1 and 1. How do we fill this section? You go to the individual matrix, you look for 1, 1, and then you try to look for 1, 1. There's no more 1, 1, right? So 1, 1 is an intersection point of this one. So you copy 1000 into this location. Okay. Then you look for second one. 2, 1. So 2, but there's no 2, 1 here. So you cannot find 2, 1 here. You put 0. Then you continue. You go to 3, 1. Look at 3, 1, 3, 1. You get negative 1000. So you write, okay, look for other also lah, because I know there's no 3, 1 here. So 3, 3, 3, 4, 4, 4, 4, 4, 2, 2. So you have negative 1000. Okay, so then I go for 4, 1. 4, 1. So I look for a number above the matrix. So 4, 4, 3, 4, 4, 4, 4, 4, 2. So 4, 1 I don't have, so I get 0. Any question so far on the procedure that I show you now? No question, I'm going to ask question at the end. Okay, now this question is for Lai. Lai, what is the number in this location? What is number for 1 and 2 location? What is the answer? Lai, are you there?
$2,000.
Why 2000? Explain. You don't guess, you know, there's a logical way of finding it. I just explained just now. It's like playing Lego. Okay, can you explain how I get 1000 here? Lai, explain. How do I get 1000 here?
One and then 1, 1.
Okay. Now solve for this location. 1 and 2. Find 1 and 2. Can you find it?
Negative 3,000.
Where's the location? Where on the screen you see 1, 2? Show me.
Is it the last one?
This one, last one.
Cage.
This one.
Yeah.
How you see 1 here? Explain.
Okay. 2. 1, 2.
What number you see here? What number you see? What number you see here?
4, 2.
4, 2. Then how come you can see 1? How come you can see number 1? Or are you seeing something else?
2.
I'm not seeing 1 here.
Yeah.
So is there 1, 2 here inside this 3 set of number here? Is there 1, 2? Are you seeing 1, 2 here?
No.
Yeah. So if you do not see anything, what number you put?
0.
0.
0.
Okay, 0. Okay, I'm gonna let you go for a while. Okay, I'm going to ask Singi. Singi, what number should we fill inside here that I show on the screen here? What number should I fill in here?
3,000. 3,000.
3,000 Y. Yeah. Okay, because combination of 2 and 2, we can find 3,000. So correct, 3,000. Okay, Katana. What is the value this location? 3, 2.
0.
0. Correct. So I assume all of you know how to fill in already. Okay. So sometimes there's an intersection of number. Sometimes you have two number. We have one example later on. So sometimes the location there, you need to look carefully on the matrix that we have here. So if you have one number above, you pull in there, one number below, you pull in one there, or there also. We will look at that example sooner. Okay, so this is a step that I'm trying to explain just now. So at the end, we'll get this set of matrix by looking at the individual matrix here. So what is special is this number. Okay, why we have 1,000 and 2,000 here? Because we have an overlapping of matrix here. So textbook calculation, we put U1, U2, U3, U4. Here is just to conveniently to pair up with the displacement later on. Okay, so you can still use 1, 2, 3, 4 that I showed you just now. I just to try to explain why you will see 1,000, why you will see 1,000 plus 2,000 over here. So if you check the matrix, okay, if you check the matrix, we have two number appearing 2 times in the individual matrix here. So this location is 3, 3. So you go for 3, 3, and then you look. Here we also have 3, 3. Here we don't have 3. So the first set referring to first element. K1 means first element. Second one is referring to the second element. So the first set, 3, 3, we get the first number, 1,000. So you pull 1,000 here. Then the second set, 3, 3, you get 2,000. Pull 2,000 inside here also. That's why we have a plus sign here. It's an overlapping of two matrices. So we are actually sum up all the individual matrix into one very big global matrix. So this is the procedure that we do. And then okay, my question is that this number 2,000 plus 3,000. Okay, Singi, you able to understand 2,000 plus 3,000 of this number? How we get this one?
Yes.
Yes, huh? Lai, are you able to understand why we get
Yes.
2,000 plus 3,000? Correct, huh? Okay, Katana should be no problem, right? Katana,
Yes,
you're
sir.
right. Okay, good. Because this is important, this is a very popular question, or can say it's a popular procedure that we're going to evaluate student. So be careful when you combining individual matrix that you see on the screen here on the left hand side, on the right hand side. You combine these three into a global matrix. All right. And then you write the total answer. All right. You just combine 1,000 to 3,000. This one 2,000 to 5,000. Then you get a complete global Stiffener matrix. Okay. So I expanded this one just to show you that there's a overlapping of number. Okay. So in exam, when it comes to answer, I ask for section 1, I ask you for global Stiffener matrix. There's one more line of answer where you repeat this one, but you sum up the number. Okay, understand? So you don't give me this step, but if you give me these steps, I will give you not a full mark. Right? For example, if you give me until here, the full mark for answer is 2 mark. So if you read under here, I will give you 1 mark only. Not complete. So a complete answer, you should copy all the numbers, and this 3 location, it should be 3000 rather than 1000 plus 2000. This is just an operation. And then 2000 plus 3000, we should seeing 3000, 5000 in your answer. Okay, so if you give me all the number here in the matrix, then you get a full mark. Okay, right. This equation will give you 1 mark also. This equation is a general operation procedure where it tells the examiner or the marker what you do with the answer, how you get this answer. You tell the marker that actually to find the global stiffness matrix, you take the individual stiffness matrix K1 plus K2 plus K3. You just tell the examiner that you understand what you're doing. Okay, you will get 1 mark here. All right. Yeah. So any question for section 1 so far? We already solved for section A. Ask me question if you're not sure. How all these numbers come into place is still not clear. You can ask me. And this topic is very important. This procedure is also called superimpose. Now we are looking at a simple spring structure. Later you will see a more complex structure, which is in your question number 11 and 12. Maybe question 12 will be more complex. Okay, so make sure you understand these slides or this screen. Everything makes sense to you, because in the exam all this number will change. The important is the concept that you understand. Okay, no question. We move to the next one. The next one, we're going to find displacement, which is, again, recall F equal to KD. I use a small one because we are looking at an element. Oh, sorry, we are looking at node. So, by the way, later on, we're going to change. You have F, K, and D also. Okay. Yeah. Okay. Now, we're going to write the general equation we have. F equal to K D. So in exam, if you write this one, the general information, you write, if the question asks you to find displacement and you start with the global stiffness matrix equation, you write capital F equal to KD with the correct symbol, you'll get 1 free mark here. Okay, without solving, you just write this general equation, you get 1 mark. And then you expand this general equation into the one that in a question. So what you write is, you have F on the left hand side, you have F1, 2, 3, 4, 1, 2, 3, 4. Why we have 1, 2, 3, 4? Because we have 4 nodes. We have 1, 2, 3, 4 nodes here. Okay. Then stiffness matrix, I don't need to explain anymore. We already solved for in section A. Just copy from section A. Again, this is just to remind you that the number for row 3, column 3, row 3 number is a combination of 2 matrices. Okay, combination of 2 matrices. And for your displacement, remember to change to the direction. So in this case, it's X. So you have your U symbol here rather than D. Don't use D in this section. Okay, use according to direction. In this case, you have X, so that's why you use U. So you have U1, U2, U3, U4. Okay, this one should be direct. Any one of you want to ask me question? Anything on the screen here that look weird to you? Make sure you understand that. Now we want to solve for displacement, right? Okay. Now you recall, we have homogeneous and non-homogeneous. Okay. What mean by homogeneous? What mean by homogeneous? When you have a homogeneous case, what does it mean? Lai, are you there?
Yeah.
Yeah. What is homogeneous case? We have two types of case, right? Homogeneous and non-homogeneous.
Okay.
You forget? This morning I just refreshed you like 20 minutes ago. Okay, let's try. Katana, you can remember what is non-homogeneous or homogeneous? Which one you can remember?
If it's homogeneous, that means there's some displacements that are zero.
Okay, correct. Means there's no displacement, correct?
Okay,
You mean
yeah.
there's no displacement? Yeah,
Yeah.
correct. So yeah, again, Lai, you need to keep up. So homogeneous, it means that we have some part in the structure that don't have displacement, means doesn't move. If you don't have displacement, mean doesn't move. So if we have homogeneous, mean all the point that we have here is moving. So we have all displacement. Now you understand? Lai, do you understand?
Oh, yes.
Okay. Now I'm going to ask you, Lai. So looking at the screen here, at the bottom there is a diagram. I look at point number one. Point number one on the left. So point number one is homogeneous or non-homogeneous case. You say you understand, right? So explain. Does point one is homogeneous or non-homogeneous?
Homogeneous.
What was it? What's the answer?
Homogeneous.
Why homogeneous? Why? Why
Because
homogeneous?
zero, right?
What zero? What things zero?
The x-axis.
X-axis zero. Katana, can you explain to Lai? Point number one, is it homogeneous or non-homogeneous or homogeneous, and why? Why is the reason?
I would say homogeneous because the point one is attached to a fixed station, so it won't move. The displacement would be zero.
Correct. Lai, do you understand what Katana trying to say?
Oh, yes.
Yes. So does point one move or not, Lai?
No.
So is there displacement at point number one? You
Yes.
understand the word displacement or not? Do you understand the English word displacement? What does displacement mean? Don't feel shy, in this module, don't feel shy. Don't think that you are asking some stupid question. If you don't know, then you don't know. I will try to help you to understand, because when you go to work later on, I think you've been through internship already. So if you don't understand, don't worry about stupid question. You learn. You come to university to learn, and it's my job to teach you. Okay. So displacement, the word you see on the screen here, this is the English word that I keep using. Displacement is the changes of location. So if you pull something, point number 1, if you pull it, this point we're going to move. So this is the displacement. This is the thing that we are talking about. Displacement. In the Stiffener matrix, D represent displacement. So it's in the X, we will use U to represent the displacement. Do you understand, Lai?
Oh, yes.
No, okay. I'll keep asking you question, Lai, until you really show that you can able to answer confidently. Yeah. Yeah, because you are my student, you should be proud to be Dr. Ang's student. So unless you don't want to tell people. All right. Now, the next steps after you call back the general equation, F equal to Kx, you apply the boundary condition, homogeneous boundary condition, U1 equal to 0, U2 equal to 0. Because, why? Because this is a very straightforward, why we want to apply boundary condition? Because we want to simplify the equation we have. We want to remove all the unknown that we do not know. So in this case, we know that point 1 do not move, point 2 do not move. So U1 equals 0, U2 equals 0. So if you look back the equation on the top here, straight away you remove 2 equations already. U1 0, U2 0, you only focus on 3 and 4. Okay, this is the reason why I keep repeating what is homogeneous, why we need to apply for a boundary condition. Okay, I'm going to 1 or 2 more slides, then we go for a short break. Okay. So when we apply the boundary condition inside the equation, we focus on 3 and 4 because the question also got us to focus on not 3 and 4. So I already highlight something on the screen here. You will see a dash line, dot line or dash line on the screen here. You will see that when we have boundary condition 1, 2, 0, we focus on U3 and U4. So just now when you label your matrix, if you can recall, because 1 and 2 is 0, we only focus on component 3, 4 here, and force 3, 4 here. Okay, make yourself try to like understand what you're trying to do. After applying boundary condition, we look at the general matrix, and then we try to find the easy way to solve problems. So in this case, U1, U2 is 0. So the only left out is only 3 and 4. So you look at 3 and 4 component here, the 3, 4 component here. Okay, we try to make things a bit more simpler. Okay, I pull out the remaining matrix. So on F3 here, you see F3, right? So note number 3, if the point is free to move, if any point or any structure that free to move, all the force at this point, for example, point 1, point 1 here, all the force in point 1 is 0. If the point able to move, okay, for example, I draw a car. So if this car is free to move, you can push this car from behind. Means all the force inside this whole system equals 0. There's no force, balance force inside this question. Okay? If this car free to move in x direction, so all the force in x direction equal to 0. We assume there's no friction, and if you push, this car going to move forward to the x direction, then all the force inside this system equal to 0. Okay, by having this kind of concept, you will know straight away you can apply F3 equal 0, because if you look at this point, these 3 points, point number 3, even you try to pull at point number 4 or point number 1, point number 3 still free to move to the left and right. And we are focusing on capital F here. It means global. Global dimension, if the point is free to move around, there's no force in that particular point. So there's a reason why we know that F3x equal to 0 and F4x equal to 5,000. Okay. Why there is a 5,000 there? Because the question already gives us there's an external force at point number 4. So this capital F is a global dimension, meaning you're looking at the outside of the system, and outside the system there's one external force, which is 5,000. So you apply 5,000 inside the equation. And then here, why this one becomes 3,000, I already explained, or self-explainable. Then this one, why become 5,000, also self-explainable. And you copy U3 and U4. So here, this equation, okay, lie. If you look at this matrix, 0, 5,000, 3,000, negative 2,000, negative 2,000, 5,000, U3 and U4. How many linear equations you have in this matrix? You have 1, 2, 3, 4. How many equations you have in this matrix? I'm asking about this matrix. How many equations you have?
2.
2. What? How you know 2? How you know 2? Now, there may be someday your junior come and ask you, how this one, how you know it's 2? Two linear equation, or two you are solving 2 simultaneous equation. You should able to explain to your juniors and expect when you go to work, your intern, maybe you're already a full-time staff and your intern will come and ask you, or you try to ask your intern to solve some mathematical problem. How you know this one is a 2 linear equation or 2 simultaneous equation? How you know? Okay, Katana, you understand why this one 2 equation? Katana, you understand?
Not very sure. Maybe because the biggest matrix is a 2 by 2.
Correct. The answer is 2.2. The matrix here is 2 times 2. Okay, and we already explained how you get how you convert. Okay, I need to go back to our previous slides. We already explained how to get. Okay, this is an example. How we get 3 equation into 3 times 3. How we get these 3 equation into 3 times 3. And we already explained how we get 2 times 2 from these 2 equation. Okay, go and read my slides. How we know that we have 2 equation inside this matrix, because we convert equation 1 that you see on the screen here into this format. This one also. That's why we have F1x, F2x on the left hand side, Stiffness matrix, we have 2 times 2, and we have 2 displacement, U1 and U2. Okay, right. Let's just complete section B, then we go for a break. Huh? That's right. Okay, polish up your mathematics skill. Okay. All right. So, Katana, do I explain? Do I show you the answer? How we know that this one is a two? There's a 2 equation there just now. Do you see the I'm trying to explain? Katana, do you understand?
Yes.
Yes, huh?
Yes.
Okay, Lai, do you understand which slides to go if you not understand?
Oh, okay.
Okay, yeah. Singy, I know you no problem. Okay. Okay, we continue with solving the problem. We're going to solve U3 and U4. So solving this, you get the displacement, meaning you need to do the inverse matrix. So what you do, you move. Okay, here we have F equal to KD. You want to solve the displacement. You move this one to left hand side. You will get K minus 1 F go D. Okay. Apologize for this one, right? So how to calculate the inverse matrix 2 times 2? Go back to your mathematics handbook. There's a procedure to process this one. So at the end, you get U3 equal to this number, U4 equal to this number. Okay, let me stop the recording and go for a short break.